This is Project 6. We are Group 6.
So if you take a look first at our slow cooling, we'll see that this phase diagram over here for gold, as you go this way along the graph, it'll be increasing in percentages of gold. And then if you go this way, it'll increases in temperature. So if you follow up this, above this line here, it'll be in a liquidous state. But if you go below it, it'll be in a solidus state. So if you follow along, we have multiple points regarding temperature. As temperature decreases for 40% right here, we'll see that point A correlates to right here. So it's a completely liquidous state. So there's no cooling formed and there's no solids at all. And then we go to B, it hits the first point in the solidus. So in between here is a two-form solution. So we'll see that it starts forming uniformly within the middle of here. And as we get C, we decrease the temperature further. We'll see that the atoms are forming and they're getting solid in an equal equilibrium. So this here is entirely 40% solid for gold, but out here in the white, it'll be the lower. And then as we keep going down, we see D, more solids are formed, and all of these shaded areas is going to be the 40% since it's cooling in equilibrium. And then as we completely enter the solidus state, we'll see that the entire thing is in one form and it's in just 1%. So if we move on to the fast cooling, we'll see that with this same phase diagram, liquidus, solidus, and then the two-phase area, we'll see that if we cool it fast, there's methods such as quenching. If we look again at A, it'll still be liquidus, but as soon as we enter into the B, where it'll be in that two-phase solution, the highest percentage right here, or the lower percentage, it'll freeze first. So then we get to these points where the lower percentage golds are forming first, since their melting points are going to be lower. And then as we get onto C, we'll see that this middle part is already frozen, so it's already there. So then the next percentage gold will form on top of it. And then as we keep going down, we'll see that layers are forming on top of the layers that have already been formed. So right here in the middle, if we go all the way back down to E, we'll see that the middle is a different percentage of gold than the outside, and that correlates to the different melting points of those different percentages. And that's why these layers are formed within the structure. So then if we move on to an example where we take it from 1200 degrees to 1000, at 1200, it's going to be above that liquidus line. So it's going to be in a state of liquid. And then if we go to 1000, it's going to be in between. So it's going to have two phases. So there's a certain way to figure this out. So if we take a look at this, this will be the liquidus percentage minus the 40% that we were starting with. And then this is the liquidus minus the solid percentage. So if we go back to the original, we'll see that this correlates with the 50%, or 40%, and then this right here is where the 40% is originally, and then this is where our 30% will be. So if we take that and go put it in the equation on the next slide, we'll see that if we plug these numbers in from 50 minus 40, and then 50 minus the 35, we'll get a ratio of 10 to 15, which is 0.67. So this is telling us what the percentage of the gold solid is in our form, and when it's at 1000. But so if we know we're starting off with 1 kilogram, and we have 0.67 of it, we know that the liquid, we're missing 0.33. So the liquid takes up 0.33 kilograms, and the solid takes up 0.67. So then we take this on, and we find the actual masses of each portion. So the percent of masses in solid is going to be that 67%. And then we take that percent times the 35. We'll get that we have 0.233 kilograms that are in forms of solid. And then if we take that and do it the same with liquid, we'll see that we take the 0.33, multiply that by the 50 over 100, it correlates with the percent gold that it's at, and that'll give us a 0.166 kilograms. And if we add these two numbers together as just a quick check, we'll see that we have 0.4 kilograms. So if we have 40% gold of a 1 kilogram system, and we should get 0.4 kilograms, so this does check out.
So using this alloy, we're looking to mimic the braid. So how do you do that? So by using the resistance of the alloy and the electrons within it, you're able to assign a charge to different synapses that you might make. So you take a section and you give it a charge in order to create kind of a memory. So that would be just either giving it a positive charge, say for 1, or a negative charge for a 0. And by doing that, you can create a form of binary code that will hold on to that charge, and it'll remember it and be like a brain. It'll create a memory. So the reason we can do that with this alloy is that the electrons inside silver are extremely mobile. So they're able to move back and forth from that, either being a negative, like holding that negative charge, or holding that positive charge. So the alloy can mimic the brain by changing the resistance and charge of these kind of areas that you're charging. And this alloy is really good at holding those charges, so that's what makes it so good at mimicking the brain when you use it. So if we move on to comparing the two, we have over here, we have the phase diagram for copper and nickel, and then we have our gold and silver. So these are different kind of perspectives of the graph. It's a little bit different for temperature and for the percentage of the alloy, but it gives us a pretty good idea that this distance between the lines over here is a lot smaller, and it's a lot bigger over on this side. So what that means is that the transition over here is going to be faster, which allows it to change that charge more easily. So it'll accept that charge more easily, which makes it better at creating those memories and being either that 1 or that 0. The copper nickel has a lot bigger of a band gap, so it's not band gap, but just distance. So it's not going to be able to change that charge as well. It won't be able to hold those memories. So like I said, the ions over here are more mobile, and gold and silver are extremely conductive. So that's what makes them good at being or mimicking the brain. The more conductive the materials are, the better they'll be able to hold that charge and resistance and then hold on to that memory.
So now we're going to solve for the density of gold and silver based off of their atomic weight, atomic radius, and their crystal structure. Here, in this case, we're going to be assuming that both are an FCC crystal structure, which is a face-centered cubic structure. So if we go in our book, our material science textbook, we'll find the values for the atomic weight and atomic radius of gold and silver. For gold, the atomic weight is 196.97 grams per mole. The radius is 0.442 nanometers. And for silver, the atomic weight is 107.87 grams per mole, and the radius is 0.1445 nanometers. So this will be the equation that we're going to use to solve for density, with rho being our density. And so these other variables here are the lowercase n, which stands for the number of atoms in the actual FCC structure, and capital A is the atomic weight, which we saw on the previous slide. Vc is the volume of the specific FCC structure, which in this case is going to be centimeter cubed per unit cell. Same for the number of atoms. This is going to be atoms per unit cell, that unit cell being the FCC structure itself. And Na is Avogadro's number, 6.022 times 10 to the 23 atoms per mole. So now, by looking at the crystal structure, we can solve for Vc and N, which is the volume and the number of atoms in this structure. So if we look at the structure, all these pieces, if we added them together, those are the amount of atoms that are in this crystal structure. So if you add all these pieces together, you'll find that this FCC structure has 4 entire atoms within it. Now, since we know this is an FCC structure, we can solve for its length if we know the radius of these atoms, which we do know the radius. So we could solve for one of the side lengths of this cube, but we want the volume, so we can cube this length value to find a equation for the volume itself. So here we have Vc is equal to 16 times the radius cubed times square root 2. Now we put this into our density equation here. So for R, in this case, we're going to be solving for gold to start. So this R is going to be the radius of the gold atom. So when we put all of our numbers in, and here what I've done is I've also converted the nanometers to centimeters just to make it more reasonable of a number to use. So when we put everything in, we'll find that our density, when we solve for, is 19.28 grams per centimeter cubed, which is very close to the actual value of 19.30 grams per centimeter cubed. And now we do the exact same thing for silver. We take our volume equation, we put it in, we put all of our numbers in here, as we see. Again, I converted to centimeters instead of leaving it as nanometers. And then we solve for the density, and here we get 10.49 grams per centimeter cubed, which again is very close to the real value of 10.50 grams per centimeter cubed.